Hello, I'm Daniel Chibotero. I'm the Chief Architect for Hailo Technologies. And today we will discuss scalable and power-efficient architecture for deep learning at the edge. So my agenda for today is starting in a few words about Hailo, then discussing common pitfalls in edge AI product marketing, then looking at some real edge AI products and their requirements and trade-offs, then discuss how Hailo achieves power efficiency and scalability, and then a short walkthrough through the current available Hailo products. So Hailo is a fabless chip company founded in 2017, and our product is an AI inference processor for edge devices. We are based in Tel Aviv with offices around the world, in the US, Japan, Taiwan, and Europe. Our product is based on our patented structure-defined architecture. We have more than 130 employees, and we raised more than $88 million with the NEC and ABB as strategic investors. So our first chip, our first product, the Hailo 8, is in mass production now. Again, it is based on our proprietary novel structure-defined data flow architecture. It boasts 26 stops, and at the most common deep learning benchmark, Resonant 15, it reaches more than 1,200 FPS at 3 watts. So if we are looking at the booming edge AI landscape, we see that these products are marketed with 3 major figures. First one is the tops. These are the usual product marketing you get with tops. AI accelerator has X tops. The second one is power efficiency. So new chip has Y tops per watt power efficiency. And the third one is the number of FPS, usually at the Resonant 50 benchmark. And as you can see in the previous slide, we do the same. And from product perspective, these 3 figures are not interesting, and they will show why in a second. So first, tops. Tops is basically a figure that is based on the silicon properties of the chip. It is the number of multiplying accumulators that are implemented in the silicon times the frequency these multiplying accumulators are running at. And in most architectures, these max cannot be fully utilized for most of the workloads. And the AI accelerator architecture greatly influences the compute utilization. So here on the right, you can see 4 products for AI accelerators, the Hailo 8 with 26 stops, the new Mythic product with 35 tops, the NVIDIA Xavier NX with 21 tops, and the Qualcomm Snapdragon 888 with 26 tops. And you can see that though Hailo doesn't have most stops of the competition, it still reaches a higher FPS on the Resonant 50 benchmark. And if we go to the metric of how many multiplying accumulators are actually utilized in this benchmark, it is evident that the Hailo 8 mark utilization is higher than competition. NVIDIA is the closest competitor with this mark utilization. However, the NVIDIA benchmark runs at higher batch than the benchmarks of all other competitions. So we guess that at the batch 1, which is the usual batch number for edge products, this number will be lower. So number of tops won't get you to the actual performance of the chip on real workloads. The second marketing figure is tops per watt. And these figures is not well defined. For some products, it's the total TOPS divided by the TDP of the product. For other products, this is a power measured on some synthetic workload that is toggling almost all the max. And as I said, toggling all the max is not achievable. And the actual metrics that Edge AI products care about is probably measuring an ensemble of benchmarks, measuring the top throughput and the dissipated power for these benchmarks, and obtaining this figure, frames per second per watt, or FPS per watt, for this ensemble of benchmarks. And why does it matter? Because in the edge, the product power budget is usually the limiting factor for many products. Because many products are passive cooled and doesn't have a ventilator or a fan. And also, most products are constrained by the device junction temperature that going beyond the central temperature may harm the device. So usually the questions that we get is, what is the maximum FPS that I can get for a given power budget? And most importantly, at specific benchmarks, can we scale down the chip's power consumption if I scale down the FPS required from the specific workload? So the third metric is benchmarks, and almost all chip vendors quote the ResNet 50 benchmark, which is very old, outdated, 5-year-old classifier. And as you can see here on the right, for real applications, a classifier is not very good. You get a picture and it tells you what's in the picture. However, when we look for a more modern benchmark, the YOLO V3, which is a 3-year-old detector, this can correlate with real workloads that run in the edge, as you can see on the right. This is a multi-object detector, detecting 4 objects in this image. But again, it's a 3-year-old benchmark. And usually customer workloads try to make use of the most modern state-of-the-art networks because the research in this field of deep learning is rapidly evolving. And as you can see, actually YOLO V3 was the state-of-the-art object detector in 2019 and 18. But in 2019, Efficient Det by Google outperformed YOLO V3. And in 2020, YOLO V5 outperformed both. So sticking to a specific benchmark won't do any good because the research in this field evolves very quickly. So then we get to the Edge AI product trade-off. You can be very accurate on your workload, but then you will probably dissipate a lot of power and throughput will be lower. You can sacrifice accuracy and maybe gain low power and higher throughput. But each Edge AI product tries to balance these 3 metrics to meet its product requirements. So let's look at a few Edge AI product requirements that we've got and see how Hailo manages to implement them with the Hailo 8. So the first one is a company doing a camera pole, multi-camera situated on a pole and processed with the video analytics. So here the requirement was for a very accurate object detector with more than 40 MAP. MAP is the market metric for the accuracy of object detectors, 6 independent streams running at real time of 30 FPS, and a power budget that is lower than 5 watts. So again, for edge, this company decided to sacrifice the power, draw lots of power comparably to passive cooled device, and gain of throughput and accuracy. So using a host processor, 6 cameras, and the Hailo 8, and the YOLO V5M network deployed to the Hailo 8, we are able to achieve these product requirements for these specific products. So we are running a Hailo YOLO V5M at more than 190 FPS on the Hailo 8 with a power consumption that is lower than 4 watts. The second product is a video analytics platform that requires real-time processing of 16 independent streams, but here the workload is a person detector, and therefore the accuracy can be sacrificed to gain high throughput and low power. And in this case, though the Hailo 8 is able to run a detection network, the MobileNet SSD V1 at more than 1000 FPS and 2 watts, to meet the requirements of this specific product, we are able to scale down the throughput to 480 FPS and scale down also the power consumption to 1.2 watts, showing the scalability of the power with the throughput. The third product is a mobile robot. It has a single sensor running at 60 FPS, and it should run concurrently both semantic segmentation and object detection networks. And here we have a latency requirement, less than 30 milliseconds of sensor to perception latency, and less than 3 watts power consumption. And for this robot, we connected the camera directly to the Hailo 8 CSI interface, streaming the sensor data directly to the Hailo 8 chip without going through the host processor. And this eliminates the need for frame buffer and reduces the latency. And in this product, the Hailo 8 runs concurrently a CenterNet ResNet 80 object detector at 60 FPS and ResNet 80 FCN 16 segmentation network also at 60 FPS, and the resolution is higher than HD ready. And for this whole system, the power consumption is around 3 watts. So when you try to target an edge AI product, you are asking, okay, if I have a power budget of 3 watts that is can be usually cooled passively, what is the throughput and the accuracy trade-off that I can get? And here, Hailo showcases a range of networks from low accuracy, high throughput MobileNet V1 running at more than 1000 FPS, but at around 20 MEP, to the most modern YOLO V3 and YOLO V5 running at around 40 MEP accuracy, but lower throughput. So how do we get to these impressive figures? So again, our architecture is structure-defined data flow architecture. We take the neural network and we map them layer by layer to the specific resources needed to implement the requirements of this layer to our silicon. And our continuously evolving software is offering efficient mapping to the evolving network landscape to our chip, and constantly broadens the offering of our power, accuracy, throughput trade-off for the end user. So first, I would like to discuss power efficiency. The main secret sauce of gaining power efficiency is not to move data much around the chip. So firstly, we don't move almost at all data off chip to external DRAM or host processor. And also the proximity in the layers in the network translate to proximity of the layers in the silicon, and data moving throughout the layers moves at a very small distance through the chip when moving from layer to layer. In addition, we have implemented relevant power states of resources in compile time if resources are not used by the specific network. And also resources may change its power state in runtime if the resources are idle for some time. In terms of scalability, the major two blocks that may end out in data flow architecture are the control elements that implement the various layers in the neural network, and the memory, on-chip memory that may be depleted with high parameter count or high activation bandwidth. So in terms of control, we enable multiple neural network layers to be orchestrated by a single control element in our chip. So this is the neural network layers. We are merging them to a single layer in our toolchain and then mapping resources that are needed to implement these two layers together. And using this method, we don't run out of control elements in our chip. And in terms of memory scalability, we are allowing the storage of layer activations of parameters to be stored on host memory. And in this case, we are able to scale to a high parameter count layer or a high activation memory footprint of networks. So our offering currently is the Hailo 8 as a chip on board, and the different modules that can be plugged in to compute platforms to shorten the time to market to get AI acceleration. The most and the newest prominent offering is the A plus E key, which is very small in dimensions and can't fit even in laptops and get AI acceleration. And also we have additional M.2 keys and the mini PCIe for other platforms. In addition to the hardware, we also ship freely out of the box deep learning applications that can run at the edge, showcasing our high performance, and the end user may take our chip and module, unpack this software offering, which is called the Tapas, and run out of the box semantic segmentation or pedestrian detection or multiple person pose estimation on his hardware in a matter of hours from receiving the hardware. So thank you very much for watching my discussion about scalable and highly efficient edge AI processor, and see you.